Hi, I'm Kees. It's spelled funny, but it's pronounced Kees. It was named after my Dutch grandfather. I just wanted to cover the state of Linux kernel hardening. This is an effort that started way before the official project was originally announced. But I announced it in 2015 to try to get everyone under the same umbrella. So this is sort of like a 10-year retrospective. If you want to follow along with slides, that's the URL and QR code for it. As a reminder for why we try to make Linux secure, you could read this fabulous book, which is about the cyber weapons arms race, which is people trying to break security, and a delightful quote that I enjoyed in it, which was, "The most likely way for the world to be destroyed, most experts agreed, is by accident." That's where we come in. We're computer professionals. We cause accidents. This is attributed to Nathaniel Borstein, who created MIME. Anyway, this is Nicole Perlroth's book. So besides just the quantity and severity of flaws in the kernel or anywhere, there's this concern about the lifetime. Back in 2010, John Corbett for Linux Weekly News went back and looked at sort of how long does a bug live in the Linux kernel. A flaw is introduced, and some amount of time later, it gets fixed. So what's the lifetime? When is that flaw usable for an attacker? And he found the lifetime was about 5 years. In 2015, as part of trying to announce the hardening project, I went and did a similar analysis and came to sort of the same, if not worse, conclusion. And even when separating by severity, you could sort of see that there was still a growing lifetime. So besides just the large volume of flaws, they have this long lifetime. So this idea of just squashing individual bugs is almost completely unsustainable. Attackers have a huge window of opportunity as more bugs get added to the kernel. So I announced the Linux Kernel Self-Protection Project in November of 2015, and it's not a separate thing from Linux kernel. It's basically just a focus area like NetDev or GPU drivers or whatever. And I was trying to sort of gather all of the disparate efforts both inside and outside of the Linux kernel developer community. I stated us as having two specific goals, which was the first is to remove entire bug classes, because fixing the individual bugs, like I said, is not workable. And then to also eliminate exploitation methods. We shouldn't design the kernel in a way that makes it easy for an attacker to abuse it once they have a foothold. So it's now been 10 years of cat herding, and beyond the technical accomplishments, I think one of the big things that we ended up doing was convincing the kernel developer community at large, for the most part, that this work actually was needed. There's a quote from Linus Torvalds saying, all security bugs are just bugs. And while on the face of it that is true, security bugs have an impact in the real world in a very different way. And so convincing everyone that getting rid of bug classes was the way to focus our attention had a lot of value. So I wanted to look at who contributed, but the number of people is gigantic. In fact, when I went back looking at prior presentations I've given about KSPP, I stopped being able to fit all of the people's names on a single slide sometime back in 2017. So we grew pretty quickly. So I'm just trying to give you a sense of the organizations and people that have contributed. We've got CPU chipset vendors, we've got distros, service providers, integrators, and of course there's a ton of contractors, researchers, and other individuals who've been contributing over the years. One amusing observation trying to look at this list from before is that there have been individuals that moved from company to company and they were the only contributor from those smaller companies as they moved around. So there's sort of a weird mix of do I recognize the individual, do I recognize the company? And then you've got, larger places, like we're at Google, there's people from all kinds of different kernel teams that are sending stuff in. But of course, the big question, the work has had an impact. And of course, people say, well, prove it. But first, I'm not going to prove it yet. I need to talk about flaws in CVEs. So the common vulnerability enumeration, which is designed to map vulnerabilities to individual identifiers. This has existed for a long time, but in February of 24, the Linux kernel project itself became its own CVE naming authority, which changed how CVEs got assigned. Prior to that, CVEs were most often assigned by general purpose distros. We'd have Red Hat or Ubuntu or whoever would say, oh, this is a problem. We've recognized it as such. We're going to request a CVE for it. And that's how CVEs got assigned through this larger method. That meant that CVEs tended to have a really specific threat model associated with them, sort of from general purpose distros. And a general purpose distro might care about some, keyboard driver or USB driver that, a network file system vendor is not going to care about in their world. So from a certain perspective, the old way of doing CV enumeration often undercounted the flaws in the kernel. And I want to explain that a little bit more. So if we had an omniscient view of the collection of all flaws in the Linux kernel, and this is more than security flaws, it's just everything that could possibly have been a flaw, the universally objective omniscient view. So within that are the publicly known flaws. Because everything outside of that circle is stuff we haven't realized yet. And then there's the stuff we've fixed, including a little gap of accidentally fixed flaws, because we didn't even realize it was a problem, but it got fixed with a change anyway. And then within that, of course, is security flaws, which is a subset of that. So then there's known but unfixed security flaws, yet to be found security flaws, and of course, the accidentally fixed security flaws. And I'd put the sort of pre-24 CV enumeration in this corner, which we can zoom into. So we've got false positives. They're not security flaws. And at the bottom, there's false positives. They're not flaws at all. And then there's true positives that got accidentally fixed or identified, and then true positives that are still unfixed, even though I have a CVE. It gets messy. With the kernel.org CNA, security flaws now overlap fixes pretty closely. So if it's a security fix, there's a CVE assigned for it. And so this means we've still got the false positives, not security flaws. We've got true positives that are accidentally fixed, and we've got true positives that are still unfixed. Those are pretty rare now because the CNA basically assigns it only once it has a fix. But if we look at this, the reminder that I try to tell people when they're really focused in on the change in the CVE assignments is that our real goal in the real world is to fix security flaws, not CVEs. CVEs are just a list. They're an enumeration. As it turns out, the new CNA kind of matches the fixes we have much more closely than the prior CV assignment system did. But they end up being a different subset. So with lies, damn lies, and statistics, I use the Ubuntu CVE tracker for most of my statistics because, well, I was working with Ubuntu back in the day when we made the CV tracker, and I tried to convince their kernel team to help me identify when things were introduced and when they got fixed, so I have lifetime analysis available. But of course, doing a retrospective analysis of things that are in the CVE database doesn't work if we've switched how assignments are made. It would be very hard to map between the two, so I didn't. So this sort of stops in February of 24 and looks back in time. And I actually go back to 2010 just because that's when I had largely started to get involved in things, even though we hadn't announced officially the project. So the big one is, have we had an impact? And this is the graph I was excited to find. So this is a look at, for a given fix, like a given date in time, you look at all the fixes in the prior 12 months. And you say, what is the lifetime of all the fixes that got fixed in the last year from this moment in time, the average lifetime. And if you look at that rolling average as you move across time, as the top graph, you can actually see that our number, the lifetime of the flaws that are being fixed, is finally turning this corner and going down. It was flat for a while and went up pretty strongly at the beginning, but you can see that it kind of matched with the bottom graph is how many fixes we were making in the kernel that were, for CVEs. And this went up over time. And my first attempt to disprove this mapping was like, well, maybe we stopped fixing bugs and then we had no good signal on lifetime anymore. But in fact, the number of fixes we've been making has continued to grow. So this seems to be a valid signal that we are, in fact, pulling the lifetime finally down after only 15 years. But it is actually moving. So this is a graph I was pretty excited to find, since I've been doing lifetime graphs for 10 years now, and it always looked flat, because it was for many years in the middle. It was about between 6-7 years lifetime on average. Now this is all the CVEs looking at it, and I wanted to take a look at sort of specific bug classes over the same time frame. So just doing a simple regular expression check on the description of a CVE, I looked at buffer overflows, and you can see it's going down over time. So if I have a poor statistics linear fit of showing the straight line, of course my next question was, sure, it's going down, but when does it hit 0? So it hits 0 in 2038. And I'm like, 2038? That number should be important. That's when the 32-bit time T epic wraps. Which reminds me to go look at integer overflows. Okay, integer overflows are going down too, that's good. And they stop in 2031. So we will avoid the time T Unix epic wrap. What a relief. But the point is, they are actually going down. And then I was like, well, how about array indexing problems? Well, it's pretty flat. I wasn't happy with that. But I realized that most of the focus early on has been on the larger buffer overflow, integer overflow stuff. And it was only after starting in 2020 with Bleeding Tooth, I got super, super irate at the compilers, because the flaw here was a large composite structure in memory, and there was this array in the middle of it, this last ADV data. And the memcopy just took the length and just blasted into the address at the beginning of the array and would just keep on copying until you could overwrite the list head structures later on. You could just overwrite all the pointers, whatever. And I lost my mind. It was like, the compiler literally has everything it needs to do the memory safety checking on this. We know how big the array is. It's there. It's well defined. So we started looking at why did we not have this protection in the kernel and in C in general with the compilers. So if I zoom in on our really poor data set, I can actually see that, yes, the arrays, since we started paying attention to it, have started to fall as well. So this is great and all, but attackers haven't gone away. So where are they now? They're looking at use after free. This was a linear fit, but that's clearly exponential. Like, this is all of the research and attack stuff has now basically gone away from the easy stuff and has focused itself largely into use after free. And I thought, well, actually I have, like, we're looking at numbers here and we're up into the hundreds per year, and before I'm like, really low data points. So this is tons and tons of flaws. Where are they? A large focus has been in netfilter and Android's binder driver, and I get to pick on IOU ring just because they've made an effort to fix it, so I can call them out here. So it's kind of all over the place in the kernel, which is not a great bit of news. But we look at where this has been coming from. A lot of it's from Google's kernel CTF vulnerability and patch reward program, and that's why they've just been beating on netfilter. And some IOU ring stuff. That's one of the contributing factors to why the Android binder driver is being rewritten in Rust. I should say has been rewritten in Rust. So there's attention is being given to the use after free, but we want to sort of think about, well, what are we dealing with use after free? Because we've got the other bug classes kind of handled. And the primary issue is what I'd classify as type confusion attacks. The Linux slab allocator, the heap, the lower level heap allocator, uses pre-sized buckets. So if you have, a structure that is, 150 bytes in size, it's going to end up in the 256 byte bucket because it's larger than the 128 byte bucket. But that means everything from 128 bytes up to 256 bytes is going to end up in the 256 byte bucket. So as an attacker, all you have to do is find a dangling pointer to some object that is in a specific bucket size, and then you can find or create another allocation that overlaps it because it's a shared space in memory. For a lot of details on this, I highly recommend looking at Andre's talk last year at the Security Summit, where he goes into a lot of detail on slab internals from the perspective of an exploit developer, but it's really, really heavily focused on the operation of how the kernel tries to deal with doing allocations and where it keeps its caches of unallocated stuff and free lists and all those other things. It's a really good explanation of how all that hangs together in the kernel. So for type confusion, like the obvious solution is to not have things overlap. And so we actually ended up accidentally fixing this a little bit in the kernel with C group memory accounting. So some allocations would be tracked as counting towards the user space allocation, and we ended up having two general bucket sets. So some things got separated in half. As an attacker, you suddenly had a more limited view of, if you had a use after free in one set of buckets, you couldn't use any of the call sites and allocations coming from the C group side or vice versa. Somewhat recently, the random kmalloc caches explicitly did this work, but they did some analysis and found that 16 buckets was pretty good statistically to break up the callers. So it became harder as an attacker to figure out where things overlapped because this was both compile time and runtime randomized, so you couldn't reliably choose what buckets you wanted to deal with. And then more recently, there's config slab buckets, which tries to explicitly separate anything coming from user space from kernel allocations. Since there was this problem of, you have a specifically sized target, and you could use things like the IPC subsystem to say, copy this much memory from user space into kernel space, and you could actually tune exactly how big you wanted it. But if those are in separate pieces, separate allocation areas, they can't overlap anymore. So the difficulty of finding these kind of overlapping things becomes much more difficult. But of course, it's just an arms race, so the next step is sort of extreme type confusion with cross-allocator or cross-cache attacks, where an allocator can be caused to free an entire chunk of memory back to the page allocator and then reallocated back to the slab allocator with a different bucket size. So you just sort of have to do more work as an attacker. It takes a little bit longer to groom the heap and find the allocation pattern that you need to change where that memory is being placed. And Andre's talk gets into this a lot. Unfortunately, this is relatively deterministic. As an attacker, you can construct what you want to do and get it done. I think a really, really excellent example of this, which is extraordinarily mind-bending and is half of a sort of data-only attack almost. Jan Horn talks about doing this kind of heap grooming and pushing an allocation back out of slab, where you've got a dangling pointer back to a virtual address. Out of slab, it goes back to the page allocator, gets reallocated as a page table entry. And then, that page table entry happens to be, not happens to be, but is intentionally set up to be the page that describes your mmap of, say, Etsy shadow. And then you can poke the dangling pointer to flip the permissions on this page table entry, and now you can just write to Etsy shadow, bypassing everything, getting you root access. Jan Horn has a very detailed write-up on this, and if you don't want to sleep well at night, I recommend reading it. So the next piece is, okay, we actually have to stop virtual address reuse. We actually have to bind an area of memory to only that type of allocation. And this is the proposed config slab virtual, which does this and sort of has regions dedicated to specific types of allocations. Unsurprisingly, this comes with some performance overhead and some utilization limits because maybe you ran out of room for your page tables in the pre-allocated range, but it is all virtual addresses, not part of the one-to-one mapping. So there's kind of a lot of memory to play with. To this day, right now, sort of the best solution for this is stuff like hardware memory tagging, like ARM's MTE, which basically allows for high bits in the virtual address to be used to enforce whether or not it's a valid pointer. But for this type of thing, this ends up becoming probabilistic because you only have so many bits, but you've got all kinds of different types that you want to deal with in the kernel. So you usually have to dedicate one to being, freed memory, and this one is the page allocator, which doesn't really say what type it is, and this one's, so you run out of space really quickly, but there's very little performance overhead, and there's no utilization limits, really. So this is still a big area that needs to get fixed. But okay, so let's step away from that and say, okay, how did we actually drive down these other bug classes? And I collected a bunch of stuff I looked at over the years just to call out, memory protections and reference counters and data structures, changing the string APIs. And as you get further down this list, you notice my verb phrase becomes improved compiler to do a thing. So we've sort of stepped out of the code of the kernel itself and started looking at the tool chain. Like, can we move the burden of memory safety further into the language, into the tool chain, without having to completely change everything? So this is what Yoda has to say about the C language. It's a lot of ambiguity in the language. This is a problem. So I like to say unexpected behavior as a superset of everything that causes these kinds of bugs. This includes sort of the really specific academic phrasing undefined behavior, which is just one special case of language ambiguity. And then there's just general memory safety, variable lifetime enforcement, no safe concurrency. There's all kinds of problems with C, but the big problem is this ambiguity in the language itself. So you could just write stuff in Rust, but if you've got 25 million lines of code that you need to port to Rust, it's not going to happen tomorrow, so we still need to fix C itself. To give an example of this is a fixed problem. There's the uninitialized stack variables. This got, I think, the phrasing uninitialized carried with it for a long time this magic idea of like, well, we just can't know what's there. It's not worth caring about. It doesn't matter. But there's no such thing as uninitialized. It has a value. For the stack, it's whatever was there before. And as an attacker with control over what you're doing, what calls you're making into the kernel, it's very easy to control what was on the stack when you go back into a function. So the question is, looking at this code, there's no explicit initialization of the on the stack variable. So what does it return? It returns input times whatever was on the stack. So the solution to this, of course, was initialize everything on the stack. Like, this is a language feature. And this was really, really critical. Now, some compiler folks worried that this will fork the language. You know, there will be code that depends on zero initialization. And my perhaps pithy response was, yes, we don't want the old way that C worked. It's dangerous. We cannot predict it, but this you can predict. It's not perfect. Like, zero initializing certainly works for offsets and array indexes and you know, lengths and all these other things to push it into sort of a safe area. But it also means things like, I don't know, user ID becomes 0. Okay, so it's not perfect as an uninitialized value, but it solves a ton of problems. Going back to the bleeding tooth flaw, not all array bounds can be checked in C as it was defined. So if you've fixed all the weird glitches in the compilers, you can at least bounds check arrays that have a fixed size associated with them. But there is, of course, trailing unsized arrays. So no dimension, no bounds checking. So again, we fixed this. We changed this. We created the counted by attribute so we can actually associate the length of an array, an unbounded array like this, a flexible array, to something else in the system. Because very, very frequently, structures that are, have a flexible array at the end have something in the structure that says how long that array is. So you just tell the compiler where it is, and now it can actually perform bounds checking at runtime. And coming next is doing this for pointers. So this is a series of structures allocated off of a pointer, but the most common version is a character pointer buffer, in other words, a string. And that string has a length stored somewhere, so you can associate those together, and now you can do bounds checking on those pointers as well. So it's just about teaching the compiler how do you get to that information, because it does exist. It may not be as clean as having that original, statically defined size of the array, but you can find it at runtime in a lot of cases, in most cases. And also coming soon is us fixing this problem of having no type wrapping awareness in C. As a language, it just doesn't care. The kernel defined signed integer as wrapping because that's technically undefined behavior. We defined it as wrapping, but most of the time, if you're outside of, say, crypto and hashing and doing all these other things, you do not want your unsigned stuff to wrap around. So adding this a new type primitive, which sort of exposed via an attribute, the no-wrap attribute, we can catch this at runtime when it goes awry, which again will kill an entire class of bugs as we start using this more and more in the kernel. Our expectation is to make size t non-wrapping first, since if you're using size t, it is almost always just a length. It's never supposed to wrap around at the other side. There are cases of it which we found and we're fixing. So yeah, this is coming back to our focus has shifted over the years, and we need to remove ambiguity in C itself. The C standard itself is sort of strict and slow-moving and prioritizes compatibility over robustness. I'd say the key thing that I've found over the years now is to make any practical progress with GCC, Clang, and even MSVC is to use a magic phrase. I would like to add this language extension, and then coordinate the extension between compilers. And that's what we've done for counted by and the zero initializing on the stack. All these things are considered to be language extensions, but every compiler implements them. So as the C standard catches up with what is actually being done on the ground, they'll get there. But in the meantime, we actually have to do that work in the compiler so that we can rebuild the kernel with these kinds of defenses. And I'd also say, please just write new stuff in Rust. We've got a ton of language bindings already in the kernel. We've got entire graphics drivers, file systems, block drivers, network stuff. I mean, there is a ton of stuff already in there. So if you can use a language that already has some built-in memory safety, instead of using C, which even governments have said this is a problem, please do that. And that's sort of the end of this talk. So if anyone's got any questions or comments, or yeah.
About uninitialized variables,
Yeah.
if you initialize to some value, say 0, the thing is, if you don't initialize it, the compiler will be able to see that you forgot to initialize it and record a warning. But if you initialize it, then you can't, and then you have a bug.
Yeah. So the comment is, if we've sort of pre-initialized everything on the stack, the compiler now can't tell what was accidentally left in this unexpected state. And this was understood, and in fact, it's a separate sort of initialization in both Clang and GCC, where the warnings for uninitialized aren't affected by it. So if you don't set it, it still warns you if it can, since actually the problem with that warning is that it is wildly inaccurate most of the time. They miss a lot of stuff, whereas this pre-initialization thing doesn't get missed. And it also gets wrapped up in like dead store elimination. So if you do later set it somewhere, if the compiler can decide that, yes, absolutely, it's overwritten, it doesn't have to zero initialize it, so there's no performance hit. But you still get the warnings if they would have appeared. And this has some weird side effects with interactions with undefined behavior, because you would expect certain constructs to not happen if it was initialized as 0, but the compiler doesn't realize that it did in fact initialize it to 0, and then it does weird stuff. So we still have to avoid the weird stuff, but it does solve that problem. And you, I saw next.
In your earlier line 2 statistics, you basically had this exponential graph for the use after free. How does Rust fix that?
Rust has a lot of concurrency solutions for this. They have lifetime management. There's a bunch of stuff around that where use after free, like a lot of the other memory safety issues, just goes away because of how lifetime management is held. You can actually deterministically show that it's not getting lost and that you have proper reference counting on everything you're dealing with. So Rust will do that. And in fact, we've had several fixes in the kernel while making bindings where the C developers were like, yeah, oops, let's fix our lifetime management of that thing so it can actually be tracked by Rust correctly. And that actually improved the C side as well. I think I saw another, yes?
Do you have anything about the AI-related thing, like activities, issues, thought, insight, whatever?
About AI?
Statistic, yeah, using AI, like,
The question is, where are we on using AI for things? So we looked at this last year, and the determination was the complexity of Linux kernel is such that the sort of contextual depth of existing LLMs was not large enough to provide sort of meaningful help in anything. That said, the research continues. I know Project Zero at Google has been working on like an AI agent to do this kind of bug hunting. So it's coming along. We'll see. Maybe we can bend the lifetime graph even lower with that stuff. Back here first.
I would love to have something like the stream seccomp, but to run my patch and tell me, hey, have you considered using like object in this array or something like that?
Yeah, the question is like, how do we get good, I don't know, code practices more programmatically? The kernel has some sort of weaker tools for doing that. The check patch will sort of say, hey, don't use this API. Why aren't you doing this thing? So that's where most of that logic ends up living. It could be a lot better, and I would hope some people could help out with that. That'd be great. I saw, yeah.
Just a quick update on where the per site slab buckets are.
So the question is, when I talked about per call site, this per slab call site stuff, this one got pushed back a little bit because it became pretty difficult to do the per call site replacement because we didn't have type information in the allocator. We only had size information. So we can't do anything with alignment. We can't do anything, like there's very little we can interrogate at allocation time when all we have is a single number. And we've already run into problems with this when integrating with Rust, which needed alignment information. So we sort of had to take worst case efforts. So I put that on hold to rewrite the entire allocation system to use type information instead of size information. And that gets us some interesting fixes in itself, but that one's still in process because even converting from all these places in the kernel where we say size of something, the something is not always actually associated correctly with what we're assigning it to. So doing a large tree-wide change, I ran into so many stupid corner cases. So I kept picking up a rock and finding another rock to pick up, and it's coming, but I think we're closer because of the weird fixes that I had to make will make it possible to do the tree-wide change, and once we have the tree-wide change, then we can do per call site a little bit better. And at the same time, there's some work in Clang to provide a numeric hash of types. Like if you have a type, you can get a numeric hash out of it. It's like, well, that's similar to what the OS X is doing, and there's a lot of work there. I could talk a lot more about it. I saw some more questions. Yeah. Yeah, the question is there any information on sort of lifetime of the use after free bugs in the kernel? And from that information, can we glean anything about where those things are coming from? I didn't actually do lifetime analysis of that. That'd be a good intersection of the two data sets. I haven't done that, but when I was looking at where are they coming from, just because of my knowledge of the age of code, NetFilter tends to be pretty old code. So those are things with probably a much longer lifetime, so we're sort of seeing that tail end of really old bugs getting fixed in NetFilter. But then we look at things like IOU ring, which is super new in comparison to the rest of the kernel. So there is clearly a mix, but I haven't done that overlap. But sort of this was why I wanted to give a view of well, where are they coming from? And this is sort of the overview. I think I saw, yeah. So I could go on a lot of discussion on that. So the idea is that C has, so there's the question of wrapping behavior. What happens when you run out of the ability to represent the value you want? And the resolution is a choice. So you can say undefined behavior, I don't care, delete the whole function. Or you can say it is a 2's complement overflow, and we just wrap around when we overflow. There's also, as another resolution is, like you said, saturating, and there's trapping. So there's a bunch of different ways we can handle it. As this is designed in Clang right now, the modes are 2's complement and don't say anything, 2's complement and warn about it, or trap. So you get to pick what you want to implement. And the reason for this is we still need to build the kernels with compilers that don't support this, or versions of compilers that don't support it. So we have to have a just 2's complement wraparound. Linus Torvalds has made it really, really clear that we cannot default to just breaking the kernel. So we can't, as a default action, trap everything that fails. So we can't make that mode without having the 2's complement but warn us about it. So we need actually all three modes for this resolution style. So that's the current design for it right now.
What you use is that you add warnings, but the behavior is still the same, right?
For that would be the default. But anyone who would care about this would set the knob to please explode.
The second question was, is anybody working on adding the lifetime annotations like with attributes or something that Rust has?
Yeah, the question is about lifetime annotations that Rust uses in C, and there is work on that. I'm not super familiar with the state of it right now. If you check with me afterwards, I can try to put you in touch with the people who are doing it, but it does exist. I saw, yeah.
Is there any central place you can go to find out which versions of the compilers have which extensions in them?
That's a great question. The question is there a place that sort of documents which versions of which compilers have the various features that the kernel depends on? And the short answer is no, that's sort of baked into the build system, but that's an excellent point. We should have a summary somewhere. We should take care of that. Good. Or someone can send it to me, please. Yeah.
For this example, plus some of the other ones, what's the performance bits you see, and I'm sure that impacts what choices you make in other implementations.
Yeah, the question is about sort of for no wrap and all of the other mitigations, what's performance impact? And really it's per mitigation. It really depends on a lot of things. I called out the slab virtual because that has kind of a lot of extra work that it's doing because it's got to do a bunch of maintenance of the TLB and a bunch of other things. So it has a noticeable performance impact. As it turns out, stuff like no wrap here is almost free in the sense that most of the time, once you get from sort of the C language stuff, once you end up boiling it all the way down to machine language, like machine code, usually there's an overflow bit in a lot of architectures. And testing that bit is very fast, and even if there are branches associated with the branch, usually just goes away because it's almost always false. So the performance on actually doing the overflow checking is surprisingly low. Now, where it does create a problem is usually with image size, because now you're checking a lot of places that you weren't checking before. So you have more code being added, but the actual execution of that code tends to be quite fast. So the performance characteristics really change based on what you're mitigating. Yeah.
Given the breadth of contributors we've gained over the last 10 years or so, are you happy with coverage, or do you feel there are areas of the kernel that are just not getting enough attention?
Yeah, the question is, how is sort of coverage analysis of flaws and bugs going? I would say that, so there's the syscaller dashboard, which I think is probably one of the most coherent and comprehensive of sort of doing coverage analysis. But I'd say it's a weak point in the sense of it's hard to do reachability analysis in the kernel. And you say, sure, I've got a syscall layer, but you've also got the network layer. Yeah, you've got the hardware being attached in some fashion. There's a bunch of different things, and this has been this has plagued CVEs for a long time, which is here's this terrible flaw, and you go, does it affect me? As an integrator or whatever you're doing, and it's very difficult to do it programmatically. So I think that still is an unsolved area that people keep working on, and it's getting better. As far as overall code coverage, syscaller is decent from a syscall perspective. What can I reach from a syscall? And it'll track coverage and other things, but there's still a lot of areas, especially in I/O controls, or you can see net filter. Like there's this sort of building a complex structure to pass it into set states, and then building another complex structure to manipulate that state. Getting those descriptors written for syscaller is still an open task. But if you look at the syscaller dashboard, there are so many unfixed bugs. Most people are spending their time trying to fix those bugs or those bug classes and not really expanding on, let's find more bugs. It's like we have enough. So yeah, it's a weird space, but it is surprisingly well covered from a syscall perspective in a way. Any other questions? Yes?
Do you find the mentality changes from fixing a bug to trying to fix the class of bug to fix that bug?
The question is, has there been any change in sort of the approach of when you see a bug, you fix the class instead of the individual bug? And I'd say that on the whole, yes. I think that was one of the big reasons I sort of waved my arms a whole lot in 2015 to try to get people to understand this problem. is that people are just like, yeah, it's a bug, I'll just fix that, and didn't really think, they didn't take a step back. And I think that there's been a pretty big cultural shift for a lot of people. It's not everyone, but I think it's a lot of people are sort of saying, I keep fixing the same kind of bug. That's annoying. How do I solve this? And like, I've even used that sort of that irritation that some people have. Like years ago, there was a person showed up who's this great researcher, and he was just sort of grinding through file systems saying, with this file system image, I can crash a kernel. With this one, I can, like, finding all these size overflow bugs and allocators. And at the time, I had this huge tree-wide patch set that tried to remove sort of handwritten multiplications in allocator paths, but it was really big. It touched all kinds of stuff. And I'm like, and I'd spent months trying to figure out, how do I get this in? How am I going to convince people to take this? And Linus Torvalds, after getting like 5 of these vulnerability reports in a row in over 2 weeks, I was like, how about this? We can just get rid of all the handwritten multiplications. They'll all go away. And he was like, fine, and just put it in. So it really depends on sort of the mood people are in. But I think culturally there is an understanding that, like, oh yeah, we shouldn't even allow for that foot gun to exist. We need a different API. We need something that isn't dangerous. We need to have robust stuff. And I think that's the big change that everyone has contributed to, is sort of steering towards, oh yeah, we could have safe ways of doing things by default instead of just saying, oh, be a better software engineer. Anything? Yeah.
So one of my existential worries here is actually not necessarily the technical aspects of preventing certain types of exploits, but actually political and licensing concerns around compilers and compiler plugins in particular.
Okay.
So over the past few months, I think I've been looking at a lot of the problems you mentioned, specifically from the perspective of the client. And I think we already see it with some of the recent Apple work for Xcode, where you can, it's a real sort of, at least personal dilemma, when you write a compiler fix to prevent a class of exploits. Because Clay's licensing model is sort of proprietarily friendly, which I don't like, but speaking personally. And it's a problem I don't know how to solve, and it worries me.
Yeah.
So I was wondering if you had any thoughts.
Trying to summarize, like, the question is, how do we deal with like mitigations that are compiler toolchain based that run the risk of staying proprietary and not getting used, aren't able to be used by the general population?
Yes.
Okay.
It's like pushing more towards compiler changes
Yeah.
for security of the kernel might push people in this direction.
Yeah. So I think it is a concern, and we've actually had sort of some stumblings about this with, you know, us trying to work on changes in Clang that, for example, Apple has a whole set of stuff that they are trying to get upstream, but it's a slow process for whatever social, political, legal reasons for wrangling it out into the open. But they're well intentioned. But you could have people that just design a thing on their own in a corner and they don't share it with anyone. I would argue that looking at, you know, the ongoing work with GPL enforcement and all these other things, there's sort of nothing to stop someone who doesn't want to share from, you know, forcing them to share. That's very hard to do. So I just sort of appeal to people wanting to actually solve these problems for the world at large, and that's sort of the angle I've taken, is like, well, we just do it in public. It's the license is the license, and we'll try to make sure, you know, keep things as copyleft as we can. But there is a risk that people just continue doing this in the corner. But that just means that the rest of the world isn't protected. And I think it's our duty to try to make sure it gets implemented in all the compilers and, you know, get it pushed up to C standards, stuff like that. I'm not sure if that quite answers your question. Yeah. Okay. I think I'm out of time. Yes, no, I'm looking to you. I don't know.
I've just got one quick question.
Oh, okay, sure. I'm looking to you before you had a question.
Yeah, just, I was wondering if in the various text editors that people use, different IDEs, has anyone thought about putting some smarts in to detect when they're writing a bad pattern and give them a hint using our favorite topic, which I was hoping to avoid, but it strikes me that that might be a way just as they're writing something stupid.
Yeah, the question is, can we leverage our AI systems to watch over our shoulders while we're writing code and say, hey, stop that. That was bad code. I'm certain that exists. Whether or not it's... Yeah, for the kernel specifically. Again, I think it comes back to an earlier question about like how do we get good code patterns here, and I think that people need to spend the time to write it. You know, I think it's totally doable, and we have sort of a weak version of that already, but I think we could have a much stronger version of that that is going to get us further. I think that's one place I have seen sort of like the coding LLM stuff is a bit of an accelerator for people who already know what they're doing, not having to spend the time going, wait, where was that? Or how do I do this again? Teaching new people how to code from square one, that's much more difficult.
Well, the off by one errors and things.
Exactly.
They're not going to write fast.
Well, hopefully, like, if we can push all the problems to the tool chain, the off by one errors will go away, all that stuff will go away. But anyway, awesome. Okay, I think I'm out of time. Thank you very much.